Hello everyone, thanks for taking the time to join today's webinar, Calibrating and Operating Coriolis Meters at Service Conditions. The NEL webinars are sponsored by the UK Government's Department for Science, Innovation and Technology, DCIT. A recorded version of this webinar will be made available to you along with a copy of the slide deck after today's presentation. We'd love to hear from you, so please submit your questions at any time during the webinar. You'll find a Q&A panel on the left-hand side of your screen underneath the video feed. Your questions won't be seen by any other attendees, and we'll do our best to answer as many of the questions as we can. But if we do run out of time, we will follow up with any unanswered questions. My name's John Dodds, and I'm a bid manager here at TÜV Süd. And I've spent the last 20 years at the National Engineering Laboratory working as part of the sales and business development team. Now, as I said, today we're going to be discussing calibrating and operating Coriolis meters at service conditions. And I'm pleased to introduce you to today's presenter, Dr. Chris Mills. Chris is a senior consultant here at NEL and has led several key research projects into pressure, temperature and viscosity effects on metering systems, and in particular, the effect on Coriolis meters. So I think if you're ready, Chris, I'll hand things over to you.
Excellent. Yeah, I'm ready. Thank you, John, for the introduction. Hello, everyone. Welcome along. First of all, got the title slide here, so it's Calibrating and Operating Coriolis Meter Service Conditions. I am Chris Mills. You'll notice the date is the 26th of April. Obviously, today is the 2nd of May. Apologies, I was meant to deliver this webinar last week, but I was unwell, so hopefully it wasn't too much of an inconvenience for you to join us today, or maybe you've had the opportunity to join today and you wouldn't have made it along last week. So welcome along. So in terms of today's presentation, the agenda, obviously I had to meet the speaker. I'm going to discuss a bit about my background first of all, and then we have the background to this presentation, a bit about the NEL facilities that were used for the presentation, for the data that's presented today, some of NEL's experience, my own experience with Coriolis meters, and then try and give some recommendations, so what you should do with respect to viscosity and pressure, for example, and then some overall conclusions. Now it's 2 p.m. here in Glasgow. The time for this webinar should be approximately 40-45 minutes. That will leave us some time for questions, as John already mentioned. So at any point during this presentation, this webinar, please feel free to fill in the Q&A. Hopefully we'll get around to them at the end and I'll answer as many as possible. However, the ones that I don't cover, I'll follow up with over the next couple of weeks as well. So I'll hopefully be in touch if you leave a question. So please feel free to use the Q&A at the side. So John's already discussed me, but introduced me, sorry. But here's a picture of me from a couple of years ago. I'm a senior consultant here at NEL. I've worked here for 15 years now. Background is chemical and process engineering at Strathclyde University. A chartered engineer, and I say recently, it was actually 2020 now, so 3 years ago, completed my engineering doctorate with Coventry University as well. So Dr. Chris Mills, although I don't often use that title, although it's quite nice to have it. Predominantly work in consultancy here at NEL and also government funded research, large scale projects, both European level and UK level, looking at a variety of different topics now. So predominantly flow measurement, but we're looking at challenging aspects, so things like carbon capture, utilisation and storage, hydrogen flow measurement, and also things like high viscosity fluids, oil and gas multi-phase flow as well. So a lot of interesting topics, a lot of interesting projects over the last 15 years. So now on to the background. So in terms of today's presentation, I've got a lot of experience with Coriolis meters. NEL has a lot of experience with Coriolis meters as well. Now I started 15 years ago, which takes us back to 2008. Just before I started in 2006, NEL started to get involved in some high viscosity research. So this was operating up to 200 to 300 centipoise, so medium-high viscosity. We started to recognise there potentially was a requirement for elevated viscosity, so even higher. However, our facilities at the time could only go up to around about 200, 300. I then started 2008. One of the first projects I was involved in was upgrading our facilities to accommodate high viscosity fluids. So redesigned our national standards oil flow facility to accommodate high viscosity fluids up to 2000 centipoise. And then we conducted a government funded research project, but also a joint industry project with oil and gas operators looking at high viscosity fluids as well and their effects on conventional single phase flow meters. So that took us up to about 2010, and at that point, written a few journal papers, presented at conferences, we had definitely acknowledged and shown that there was a viscosity effect. I'll show you some of that data. However, we started to get asked about other effects of Coriolis meters. Now, Coriolis meters are fantastic devices, mass measurement devices. They also offer volumetric measurement because they also directly measure density as well. So they give you mass flow, volume flow, and density. And there was always the understanding that Coriolis meters weren't overly affected by process conditions. And that's certainly true with respect to installation, upstream and downstream straight pipe requirements. But there does appear to be an effect of viscosity, pressure and temperature. So back in 2010, a lot of customers were starting to ask us, is there a temperature effect? We are now operating at 60, 70 degrees Celsius, but we're only calibrating at 20 degrees Celsius. Is there potentially a temperature effect? So we conducted some experiments at NEL and showed there was potentially a temperature effect, maybe not as significant as viscosity, but a temperature effect nonetheless. And we wanted to explore pressure. So we created a Coriolis GIP in 2012. I led that for the 2 years. We completed that project successfully, and we found that yes, there was indeed a pressure effect, already known about the viscosity effect, and potentially a slight temperature effect. However, there was a lack of traceable flow facilities in the world that could operate at elevated temperatures and pressures. So the kind of temperatures and pressures you might operate in the oil and gas industry, for example. Most calibration facilities across the world operate at 20 to 30 degrees Celsius, relatively low pressure for oil calibrations, certainly, so below around about 5 bar. So we found that there was a need for a new facility. So we came up with an idea for this new facility, helped design it, helped build it, constructed it, and it was built between the period of 2014 and 2016. We got UK government funding, and we fully designed this facility, got it accredited, and then for the last 7 years now, it's been fully operational. We've got a lot of commercial data, a lot of research data from this facility, and I'm going to show you some of that today. So that takes us up to the present time. Just a bit of background there. So this is the elevated pressure and temperature facility, which you can see there. So I have it here in a larger image, and I've got some detail along the right hand side. Now this is a liquid flow loop. It's a closed loop design. I don't think you can see my pointer, but in the centre of the screen you can see a storage tank. This is only used to fill and empty the line, maybe when we're doing a changeover of a test meter, for example, or maintenance. We fill the line. It's a closed loop facility, so it's fully purged of all air, filled completely with fluid, and then it's recirculated around. You can see we've got two main recirculation pumps, an end-line heat exchanger. The fluid then flows through that, through our primary reference system, which is a small volume prover. That's the white equipment you can see in the lower left-hand corner. That's known as a small volume prover. It's a 60-litre Emerson compact prover. It's now a Brooks prover since they get acquired by Brooks, and is a measurement uncertainty of 0.08% as our primary, the way that we operate. Then flows through the prover, through one of three helical turbine master meters, which you can see to the left of the prover. They are the white devices, 3 different line sizes. So depending on the flow rate, we flow through one of those master meters. flows round, and then we have two separate test sections depending on the meter size. So we have a nominal 6-inch line for our larger meters in the region of between 4-inch and upwards, and then we have a 3-inch test section for meters 3-inch and smaller. This allows us to accommodate the meters and also achieve the required flow rates for that meter size. In terms of our operating conditions, we can operate from 4 to 100 bar. We have a pressurization unit there, so we can quickly change pressure. Because oil is fairly incompressible, has a low compressibility, simply adding additional amount of oil via this pressurization system, which is controlled via a feedback loop, we can increase the pressure from between 4 to 100 bar. Now, if we were operating at say 10 bar and we wanted to go up to 100 bar, it only takes around 10 to 15 minutes to go all the way up to 100 bar and achieve stability. So it can be changed very quickly, and the pressure can also be maintained throughout a whole calibration to plus or minus 0.25 bar. So very stable pressure. In terms of temperature, we operate between 20 to 80 degrees Celsius, and again we have inline heat exchangers. Because it's a closed loop system, it's a relatively small volume of fluid flowing around through the pumps and the heat exchangers, we can quickly change temperature. So we can go from 20 to 80 degrees Celsius in about 2 hours and achieve stability. In terms of temperature stability for a calibration, we can certainly achieve in the region of 0.25 degrees Celsius over an entire calibration as well, simply by tweaking the settings on our heat exchanger to maintain the temperature at the required set point. The flow range, we operate from 0.5 to 100 litres a second. As I say, we have 3 separate master meter systems. And the measurement uncertainty at K equals 2 for mass and for volume is 0.08%. The way that we would operate is you have the test section, the fluid would flow around through the prover, we would calibrate one of the master meters at the required condition, so let's say 10 bar, 50 degrees Celsius and 50 litres per second. We would then get the K factor for the turbine meter from the prover. We would then complete between 3 and 5 test points, repeat flow rate test points at that flow rate, temperature and pressure, and then we would do a post-prove again to ensure that the turbine meter hasn't shifted and is within our acceptability criteria. So overall, achieving uncertainty 0.08%. It's a state-of-the-art facility and one of the only facilities in the world that can operate at these conditions. It's fully accredited as well, so it's a traceable calibration. The other facility is the UK National Standards for Oil Flow. I don't have quite as nice an image for this one, apologies, we don't have the 3D render for this facility. But again, this is our oil liquid flow loop. Unlike the previous facility that used a small volume prover as our primary, this uses a gravimetric reference. So we have 4 separate weigh tanks of different sizes depending on the mass of fluid that is flowing over the duration. So depending on the flow rate ultimately. We also have secondary master meters. In this case, they're positive displacement devices, which are very good for high viscosity fluids. It's a start-stop system, so ultimately we like to think of it as a bucket and stopwatch type system. So we'd flow round through the tank, from the pumps, through the test section, through the master meters, and then into the weigh tank if required. We would then compare the totalised mass or volume and collected in the weigh tank, compare that against the device under test. So it could be a Coriolis meter, an ultrasonic device, a turbine meter for example. We would compare that total mass or total volume against the weigh tank. In terms of pressure, we operate from 1 to 4 bar. Temperature is 15 to 50 degrees Celsius, and the flow range is much wider than the previous facility, the EPAT facility. The flow range for this facility is 0.05 to 200 litres a second. We have a lower measurement uncertainty because we have a gravimetric system, which tends to have a far smaller uncertainty. For mass and volume, K equals 2, the uncertainty is 0.03% for low viscosity fluids. So this is for fluids below 20 centipoise. Above 20 centipoise, our measurement uncertainty is higher. For For mass, it's 0.05%, and for volume, it's 0.25%. And this is our UCAS schedule. So just to show you, facilities are fully accredited. We have our CMC, so that's our calibration and measurement capability, expressed as an expanded uncertainty, in this case k equals 2. And it also has all the various remarks with regard to the conditions, so the viscosities, temperature ranges, and you can see the flow ranges as well, and then details your measurement uncertainty. I should mention the EPAT facility that I showed you, that closed loop facility, uses a low viscosity fluid. So we use our National Standards oil flow facility for the high viscosity work, and we use the EPAT, that elevated pressure and temperature facility, for low viscosity but high temperature and high pressure experiments and calibrations. So now I'm going to show you a bit more of the actual test data. That's me covered off the facilities. Now for the test data. So this first calibration that I'm showing you here is for a Coriolis meter. Now I'm not going to name the manufacturers or the model types. Ultimately we just see them as a Coriolis meter in this case. What I'm showing you here is a 5-bar calibration. On the x-axis we've got the reference mass flow in tons per hour. On the y-axis is the percentage error of the mass compared to the reference mass. So this is the Coriolis meter mass compared with the primary reference mass at 5-bar. You can see that we're close to specification, slight under reading, but the mass factor could be adjusted. So the mass factor for this device could be adjusted, and you could bring the results up to the 0 line, whether you need to or not. It looks like a very good calibration. Now if we include the 20, 40 and 80-bar data alongside the 5-bar, you can see that there's a significant underread, and you can see that underread starting to grow with increasing pressure. So the green data points are the 20-bar, the red data points are the 40-bar, and the blue data points are the 80-bar. And you can see that at 80-bar we're significantly underreading. Coriolis meters tend to be known as being a 0.1% device, so that's our specification, to achieve around about 0.1. Some elite models can achieve 0.05%, but mostly you're aiming for about 0.1%. Now we can see there's a clear pressure effect, and we're almost 4 times the specification at 40-bar. So at 40-bar we're underreading by 0.4%, so that's 4 times that 0.1% specification. So that's just one meter type. Now this is the webinar today talking about calibrating Coriolis meters, but I can't show you too much. Simply I don't want to go through too many different meter types, but I do have an additional one here to show you today. So again, a different meter, but you can see here that we also have a significant underread once again. Now in the legend it looks quite messy. This was another experimental program I looked at to see whether zeroing or not zeroing the device appeared to affect the results. And by and large, for the higher flow rates, as expected, it didn't. Omitted the lowest flow rate, so I did collect data at the lowest flow rate, but the zero effects are fairly significant, and it's not insofar as whether we zero or don't zero, it's just the fact that the zero can be quite temperamental. So the data, there was quite a lot of scatter, so I've omitted it from this chart. I don't think it added a lot. But again, what we can see here is that there still is a pressure effect. So it's a different meter, it's a different model, it's a completely different size. You can see now we're up to 120 tons per hour, so nominally 30 to 120 tons per hour. Different manufacturer, but we're still seeing a clear pressure effect. So these are the meters being operated without a pressure compensation factor. What we recommend at NAL is you derive your pressure compensation factor via a traceable calibration at a traceable laboratory. So that's what we conduct. So as I say, there's a clear pressure effect that you can see there. So when people say, is there a pressure effect with Coriolis meters? Yes. Ultimately, it depends what the magnitude of that pressure effect is and whether it's significant. Is it greater than the 0.1% specification? For very small meters, it might almost be not noticeable because the uncertainty of the device, the size of the pressure effect are all merged into one. But for larger meters, we're seeing a larger pressure effect. So here we go, this is a different device. And what we have here, for the previous charts I was showing you mass flow rate on the x-axis. On the x-axis here we have pressure. So this is the reference pressure in bar. In the y-axis we still have that deviation, so percentage error of the reference mass. And this is all the data. So I'm showing all the data together. So you can see the data at 5 bar, 10 bar, 20 bar, 40 bar and 80 bar. And you can see that the effect is clearly linear. And that's a good thing. It's a linear effect. So thankfully it's linear, because linear means easily correctable. You can see what we have here. You can see I've put the correction overlapped. So this is the equation. You can see y equals minus 0.007628. So ultimately that's your pressure effect. You can see the intercept there as well. That's ultimately the offset. So the meter's slightly overridden by 0.027%. Minuscule. You could adjust the mass factor by that. But the first term is your pressure effect. That gives you a traceable pressure compensation factor. Now what people ask is, can it be extrapolated? So can you calibrate a device at, let's say, 10, 20 and 40 bar, derive a pressure compensation factor and then operate at, say, 80 bar or 100 bar, so a slightly different pressure? And it's a good question. A lot of people are interested in this because you don't always, you want to use a meter potentially at different pressures, and if you had to then calibrate at each individual pressure, it'd be quite costly, time consuming, and might not be the best use of your time and resources. So previously you can see that we had calibrated the device at 5, 10, 20, 40 and 80 bar. We then derived that pressure compensation factor. I've now operated at 60 bar and 90 bar, and you can see these are two pressures that we didn't calibrate at, but using that pressure compensation factor, you can see that we've got the meter well within the 0.1% specification. Now remember, the meter was slightly out of specification. It was underridden by 0.03%, hence that term that I showed you. So it's not perfect, but the pressure compensation factor is very, very good. It's really just the meter needing adjusted slightly so that to bring it in line with the zero. However, as most of the data is within plus or minus 0.05%, ultimately it's not really worth adjusting the meter unless you're looking for optimum performance. For that, I would say that's a very good calibration, and it's really just the y-axis scale making it look as if it's not quite as good as the previous calibration. So that's to show you, yes, you can extrapolate. It is possible. So yes, it can be extrapolated successfully, but to do so, you must calibrate at a traceable flow laboratory. You need to calibrate a traceable flow laboratory, and you're ultimately best to use a dynamic pressure correction, which I'm going to touch upon in the coming slides. So a question we're often asked, Coriolis meters can measure mass flow, but they also measure density. Is there a pressure effect for density? And the answer is yes. So again, I have a different meter type here. I've operated up to 80 bar again. Again, I like to pick similar kind of pressure points to use, just because they're multiples of one another. So 5, 10, 20, 40 and 80 gives you a nice linear effect. You can see that the pressure effect is fairly significant again as well. So we're operating up to 80 bar. This is the reference density, and we're under reading by approximately 1.5%, so fairly significant. So it's a clear pressure effect, but thankfully once again it is linear, so that is a good news. Linear means it can be easily corrected. You don't want a exponential correction, for example, or a third or fourth order polynomial. A nice linear correction is easy to correct and can be extrapolated. what do we reach on pressure? And not too much with respect to temperature. That's because we find that the temperature effect is a magnitude, an order less than the pressure effect. Now, if you think back to why that would be, Coriolis meters have an RTD on board, so they measure temperature and they also have compensation factors that automatically correct for it. So all Coriolis meters out of the box are automatically correcting for temperature. The same isn't true for pressure. So this is what we recommend, and I'll discuss what we recommend for pressure in a second. So we recommend that you zero the device at operating temperature and pressure. You then calibrate the device at operating temperature and pressure as found, so no adjustment yet. You can then perform that as left calibration, so you can adjust the mass factor if you have to. You then want to conduct additional pressure compensation calibration at plus or minus 10 bar to derive the linear pressure compensation factor. Apologies, go back to that previous slide there. I think the slides are timed, that's why they're changing slightly. Apologies, so let's bring this back. The Nel pressure correction is then fully traceable and meets what we're calling the Oil and Gas Authority regulations. It's now the North Sea Transition Authority, so this is the regulations for operating in the UK North Sea. Now, if I touch upon the pressure one more time, temperature is corrected by the RTD on board, however, pressure isn't. So no Coriolis meter ships with an onboard pressure measurement. You have to supply a pressure measurement to the device, or you can use a static pressure correction. Now, I don't recommend the static pressure correction, and there's a few reasons why. Very few operating conditions are static. So, for example, if you're operating at 20 bar, you might have a pressure swing of plus or minus 2 or 3 bar. Now, if you use a static correction, then you would always be correcting for, say, 20 bar, but you could then be operating at 22 bar or 18 bar if you have a 2 bar swing in pressure, which means you could be over or under correcting. So what we recommend is use a dynamic correction. So use a pressure transmitter that's monitoring the line pressure. You have that traceable compensation factor, and it calculates what the pressure compensation factor is with respect to the line pressure, and always uses a dynamic correction rather than a static correction. That's the optimum method, and that's what we recommend. Now, that's the NEL recommendation, and that also meets the NSTA, the North Sea Transition Authority regulations. Now, it can be quite significant because for certain meter types, the pressure effect can be substantial. So you could be underreading by, say, 2%. So if you're not correcting for pressure, then you could be significantly mismeasuring your flow. The same isn't true for temperature because of that onboard temperature correction factor that we find that doesn't really need adjusted. There's very little effect now of temperature due to the good amount of research being conducted by Coriolis meter manufacturers. So that's pressure and temperature. I'm now going to discuss viscosity. Apologies, I'm on the wrong slide again there. Just skip through it. So now I'm going to discuss viscosity. So there has been some other research by other NMIs, so National Measurement Institutes, designated institutes, universities, and also meter manufacturers. So some of the findings, this is a paper here back in 2006, so just around about the time I started NEL a couple of years before, and they discovered the velocity profile effects in Coriolis mass flow meters from some small scale research. They mention an important term, which is the aspect ratio of the device. So you might have heard that mentioned. The aspect ratio is the tube length divided by the tube radius. So you have Coriolis meters, typically twin tube devices, so two tubes within the device. They all have different lengths depending on the manufacturer, the model, the meter size, and obviously a different tube radius again depending on those factors. So they all have different aspect ratios. I've not included the chart, but in one of my journal papers I've calculated the aspect ratios of some common Coriolis meters from the different manufacturers, depending on their meter size, and the aspect ratio does differ. This paper here found that the aspect ratio was strongly correlated with the effect of velocity profile effects. So they found that velocity profile effects such as the laminar profile, and we're saying laminar starts around about the 10,000 and below Reynolds number. Some people quote 2,000. It depends on your entry conditions. So that was part of my doctorate research. You can actually have laminar flow persisting all the way up to 100,000 Reynolds number or so. It really depends when you have perturbations. So basically puffs and eddies creating swirls, which then creates a disturbance which moves towards less of a parabolic flow profile to more of a turbulent flow profile. We found that smaller aspect ratios have larger velocity profile effects. Some other research, so from a meter manufacturer, in this case Andrews and Hauser, they found that viscous shear forces reduce the Coriolis effect at low Reynolds number. So if you're operating at low Reynolds number, and you have this high viscosity fluid as well, or medium to high viscosity, say above 50 centipoise for relatively high viscosity to medium viscosity, the viscous shear forces start to reduce this Coriolis effect. So the Coriolis force is dissipated in the secondary circulation. This causes an underreading of the mass flow. So the effect becomes insignificant above a certain Reynolds number, but low Reynolds numbers, again, typically below 10,000 to 20,000, you find that there maybe is this effect of viscous shear forces reducing the Coriolis effect. So now I have some data to show you. Now I like to use this chart, so some of you may see it. I've seen it in my previous presentations or journal papers, but it's quite a nice set of data. So what we have here is, again, on the x-axis we have reference flow rate in kilograms per second this time, rather than tons per hour. On the y-axis we have mass flow rate error, so again that's a deviation in the device under test mass, so the Coriolis meter's mass flow, or totalised mass, compared with our reference mass flow rate or reference mass. We have 10 degrees Celsius data, and that's the dark blue. We have 20 degree data for kerosene in light blue. We then have 30 degree data for kerosene, that's kind of the yellow data point, and then we have 40 degree data for kerosene in red. Now kerosene is a light fluid, fairly low viscosity, hence altering the temperature doesn't really affect the viscosity significantly. We're in the region of 3 to 2 centistoke when we have no decimal places. Very small shift in the overall viscosity. This would be termed as a light low viscosity fluid. You can see I've overlapped the manufacturer specification, that's the dark blue lines. You can see that all the data is well within the manufacturer specification. You can see that the dark blue points above the zero line at 10 kilograms a second, that's potentially the effect of the zero shifting the results there just at that one condition. Now that's the low viscosity fluid. We now tested this exact meter, kept it in the same place, we didn't move the device, we simply changed the fluid. So from one day to the next we can change the oil fluid, the test fluid. So the results are well within specification. Changing to the high viscosity data, so in this case, this is the trade name for the fluid, and it's called Primol. We have 10, 20, 30 and 40 degrees Celsius data once again. But you can see that because it's a medium to high viscosity fluid, by altering the temperature, we alter the viscosity. So we're operating now at 50, 80, 175 and 300 centistoke. You can see that there appears to be a clear underreading. However, a bit of scatter. It's not the nicest data to try and put a trend line through. You can see we've got different polynomials for each individual temperature. A couple of what looks like rogue points here for the 30 degrees Celsius data. Again, likely to be the zero effect. Now at this point, back when we completed these results, there wasn't a lot of understanding with respect to Reynolds number effects. Most Coriolis meters were assumed to be unaffected by Reynolds number because they were not affected by installation conditions with respect to upstream and downstream straight pipe lengths, whereas a meter like a turbine device or ultrasonic might need 5, 10, 20 diameters upstream and 5 diameters downstream. Coriolis meters are not affected by the entry lengths, however they do appear to be affected by viscosity / Reynolds number effects. I'll show you that in the next slide. So what we have here is the meter being out of specification, obviously that 0.1%, all but those two rogue points you can see at 10 kilograms a second at 30 degrees Celsius, just by chance. Now we have the pipe Reynolds number effect. So you can see here, on the x-axis we have pipe Reynolds number, on the y-axis still mass flow rate error. This is all 8 data sets. So we have kerosene at 10 to 40, primol at 10 to 40, and you can see there's a clear Reynolds number effect. For high Reynolds numbers, the meter's well within specification, doesn't look overly affected by Reynolds number, but as the Reynolds number starts to decrease, there's a clear linear effect. Now, there's a few what look like outliers. They're more likely just to be simply zero effects, which you always have to be mindful for Coriolis meters. I have a journal paper that discusses, and also a good practice guide that's freely available as well on our website, that discuss zero effects. I'm not going to discuss it in too much detail today. But what you can see here is a clear Reynolds number effect. So we can see with decreasing Reynolds number, there's an increasing underread, and all the way down to approximately 300, 400 Reynolds number, we're underreading by approximately 1.5%. So very significant when Coriolis meters are 0.1% devices. So yes, high viscosity fluids for Coriolis meters, it certainly looks as if there's a viscosity, or there is a viscosity / Reynolds number effect. So what do we recommend at NEL? We recommend that you can potentially compensate with respect to Reynolds number, but you have to perform significant characterization of your device with respect to Reynolds number. So what would that look like? Well, here's what we recommend for the calibration procedure. We specify the Reynolds number range of the device. So this involves us speaking with the client to ascertain what the viscosity, what the geometry of the device is, geometry of the pipeline, what the fluid viscosity, density, and flow range is, and we can look at the Reynolds number range. We'll then try and match that Reynolds number range for high viscosity fluid at least 2 or more viscosities / temperatures. We'll zero the device at operating temperature and pressure if required. We don't always do it. I'll discuss that in a minute, because I can see you've got a question on that. We then calibrate the device at the Reynolds number as found. We decide if the Reynolds number effect is significant. It isn't always. We find for certain devices there's a significant Reynolds number effect. For other devices, depending on their aspect ratio, the Reynolds number effect can be lower. It might still be within that 0.1%. We can then perform an as-left calibration if required. So if there's an offset outside of the Reynolds number effect, we can adjust it, move it up or down. And then we can also have a linear compensation. So I've not put that linear compensation through like I did for the pressure, but it certainly is possible. So you could have a linear compensation factor with respect to Reynolds number. The issue with this is, though, you would need to ascertain what the Reynolds number is of your fluid at flowing conditions. So you need to use the uncorrected mass flow, the pipe geometry. You need to then use the density from the device, and also have a handle on what the viscosity is. Now that fourth parameter there, the viscosity, is a challenging one. People don't always measure the viscosity of their fluid. So that means having a live dynamic correction is more challenging. However, one of the main meter manufacturers has a patented Reynolds number correction, and they ascertain what the uncorrected pipe Reynolds number is and use a dynamic correction. And we've completed some research and we found that correction to be fairly robust. So that's just to cover that. Sorry, I had to go back there, my slides were moving again. Now, coming up to the overall conclusions, then I'm going to touch on some of the questions, because there's several have come in, which is good. So some of the key findings. We often get asked this: can a water calibration replicate service conditions? So can I simply calibrate my Coriolis meter in water and then operate at elevated viscosity or elevated temperature and pressure? My answer to that is no, it doesn't fully replicate it, but it depends on your measurement uncertainty. If you're only trying to achieve, say, 5% measurement uncertainty, it's a low-value product, there's no strict regulations or agreements, then potentially a Coriolis water calibration does replicate your service conditions because of your high uncertainty. However, for most applications, when you're trying to achieve a low measurement uncertainty, a water calibration doesn't replicate service conditions. Secondly, the vendor published pressure corrections are not traceable, so we always recommend that you ascertain your device's pressure compensation factor at a traceable laboratory. We find that the temperature affects a magnitude less than pressure because of the onboard temperature measurement from the device. Find that Coriolis meters should be characterised against Reynolds number if the fluid is high viscosity. And then, apologies again, my slides have moved forward. Just going to move back. And then, that's the wrong slide, right there. And this one's critical. So people often think of a device as all being the same. So an ultrasonic meter performs like this, a Coriolis meter performs like that, turbine meter performs like this. However, what we find is Coriolis meters are different depending on the manufacturer, depending on the meter size, depending on that aspect ratio, but crucially depending upon the amount of research the manufacturer has conducted. So different manufacturers will have conducted a different amount of research at facilities such as NALs with our high viscosity fluid or with our pressure EPAT facility at elevated pressure and temperature. So not all Coriolis meters perform the same. Ultimately, if you're purchasing a Coriolis meter for your application, you really want to then take it to a traceable flow laboratory to ascertain the performance. So I would just like to thank you for listening. I think that's pretty much on time now for some questions. I can see we've got a few in the chat. So, hi John.
All right, Chris. Well done. It's a subject you've been covering for a number of years. I can't believe after all these years the amount of people that are still interested in this. But it's a hot topic.
People love it,
isn't it?
People love it.
Absolutely. Right. So, and looking at the Q&A, there's plenty of questions to go through. So let's see if we can rattle through some of these because we have got a wee bit of time.
Yep.
Right. Okay. We'll start off. First one we've got here. What viscosity is considered high for Coriolis meters? Because obviously you touched on high viscosity at the start of the presentation.
Yeah, that's a good question, and a lot of people ask that as well. So that's quite a common question. What we find is there's a trade-off between high viscosity, or a correlation between high viscosity and Reynolds number effect. Now, a simple rule of thumb, we normally say it around about 50 centipoise. Above 50 centipoise is what we call medium to high viscosity, and that's when you start to notice the Reynolds number effect. At 50 centipoise, if you calculate your Reynolds number, depending upon the velocity that you're operating, you might be starting to approach below 10,000 Reynolds number when that Reynolds number effect becomes apparent. So that's why we use that rule of thumb of 50 centipoise and round about 10 to even 20,000 Reynolds number depending on entry length. So if a customer comes to us or a client comes to ourselves with an application and they're in the region of 50 centipoise, we'd start to consider Reynolds number effects and say that's a relatively high viscosity for a Coriolis meter.
Yeah. Okay.
So hopefully that helps.
You touched on zero effects. Got a couple of questions surrounding that here. When do you know the zero might be off? So when you're doing a calibration, when do you know that the zero might be an issue?
Yeah, again, it's a good question, and we often get asked that. We have a lot of experience here at NAL. I've worked a lot with Coriolis meters. I was involved in writing a lot of the procedures that we use in-house for zeroing Coriolis meters or checking the zero. I want to be clear, the method that I use or I recommend people use and that we use here at NAL is detailed in a good practice guide that I wrote. It's freely available on our website, so please feel free to download that. I'll try and summarise it just now, but sometimes it's better to read than to listen to me without slides. I mean, this is what I recommend. So when you install the device, so your Coriolis meter is installed in your line, You have it filled with fluid, you get to the operating conditions, so your operating temperature and pressure, but you're at zero flow. So you should lock in the flow by closing the valve upstream and downstream as close as possible. You then don't just simply zero the device, you want to check the zero. So at this point you should check the zero. So you do what's known as the totalizer method. I'm not going to go into a great deal of depth about what that means, but ultimately you're checking what the meter thinks it's seen, so the apparent mass at zero conditions. You then compare that with the specification. So each manufacturer has a specification for their zero stability. That's the term they use. And you compare your apparent mass, so the zero mass that you have found, and compare it with the meter manufacturers. If it's out of that specification, so if it's larger, you would then want to conduct a zero. If it's not, then I would use it. We use a rule of thumb here at NEL because we're a calibration facility, we're trying to achieve optimum performance. We look at achieving 50% of that specification, but for an industry, I'd be happy if you were up to around about 80-90% of that specification. Then for correcting the zero, the meter manufacturers again have their procedures. We have our own procedures that we use, and again, it's detailed in that good practice guide. A lot of the manufacturers, it's almost like a push button auto zero. So you've checked the zero, you found that it needs to be zeroed, and you would simply zero it. We like to do at least 3 zeros for some meter manufacturers, depending on the model, to try and get a repeatable zero value. You want it to be nice and repeatable. If it is, you can then assume you have a good zero. You will then do another zero stability check, and it should now be within specification, and then you can move on. Now, I understand that's me just telling you today quickly in two minutes how to perform the zero, but I do recommend you read the good practice guide. There's a lot more information in there.
Yeah, and I think that
Any
good
other questions,
practice
John?
guide you should be able to download. I was just going to say that good practice guide, you should be able to download that from the website. If you can't find it on our website, let either myself or Chris know, and we'll sort that out for you.
Yep.
Okay, and next one, should the live pressure be measured downstream of the Coriolis? So when you're doing your calibration,
that's
your
our
live
recommendation.
pressure readings. Yep.
Yeah.
Okay.
No, it's a good question. Funnily enough, certain manufacturers recommend that you have it upstream, but the rule of thumb for when you're designing a flow measurement system, irrespective of technology, is that you normally want to measure the temperature and pressure downstream of the device, because you never want to influence the flow conditions upstream. So we normally measure the temperature and pressure downstream of a Coriolis meter within 2 to 5 diameters downstream of the device to make sure it's relatively close, but you also want to ensure that your pressure has suitably recovered. So if you know a bit about the effect of pressure drop in a system and pressure loss, your pressure normally starts to recover. So you want to ensure that you're kind of within the required diameters downstream. Again, we aim for between 2 and 5D.
Good stuff. All right. Next one, Chris. Next one, we've got some manufacturers claim there is no pressure effect for small, and the example given here is 1 inch or DN25 meters. Is this correct? So
again, it's a good question, and yes, I know that manufacturers do say that. There doesn't appear to be a pressure effect for very small meters, maybe below 1 inch, and a lot of the manufacturers do say yes, no pressure effect. I think there might be a very small pressure effect, but it's almost of the magnitude that it's not detectable due to the specification of the flow meter, so it's achievable performance, and also the measurement uncertainty of the calibration facility. So if we were to calibrate a 1 inch Coriolis meter, try and ascertain a pressure effect, the pressure effect might be so small that it's almost not detectable. So there probably is a very small pressure effect, because what the pressure effect ultimately is, people think it's maybe like the Bourdon effect. And what we mean by that is a Coriolis meter is a curved tube device. So these tubes were straight at one point. They've been curved into their U shape, so it can be a pronounced U shape or a slightly bent shape. As pressure starts to increase, we find that these tubes are trying to straighten, they're trying to move back to becoming straight again, the board-on effect. We find that for larger pipe sizes, this effect is larger. So for smaller pipe sizes, the pipe wall is of sufficient thickness and the device is so small that this board-on effect is relatively small. So it does appear that yes, small Coriolis meters don't have a pressure effect, but again, if it was my system that I was designing, for the sake of a calibration which isn't overly expensive when you look at your potential exposure, certainly if it's a hydrocarbon that you're measuring or a high value product, I was always trying to ascertain, is there a pressure effect for this device? So I would calibrate it at a traceable flow laboratory. I'm not just saying that because I work at a calibration facility. It's genuinely what I think. I always like to see the data. It's like you say, has this been investigated? Show me the data. That's what I would like to see. That's my answer for that one.
Good stuff. All right. There's loads of questions still coming in, Chris. So we'll carry on.
That's good. That's good. Yeah, happy to carry on.
Have you studied the effects of distorted flow profiles on Coriolis meters? Is one of the questions we're going to ask.
Yes, between myself and some of my colleagues. One of my colleagues actually completed some interesting research as part of his thesis for his degree as well. He looked at Coriolis meters installed next to bends. Some of them installed vertically upwards, some vertically downwards, upstream, downstream bends. We've looked at a lot of distorted flow profiles. We find that the mass flow does not appear to be affected. The zero of the device can be, so that zero stability can be an effect. And what you maybe want to consider is if you're operating at low flow rates for a larger device where the zero might shift a lot, you might want to look more at your installation, make sure it's nice and stable, the device is clamped upstream and downstream and there's no stress on the device. But what we have found is not so much distorted flow profile, but whether your device is suitably installed with upstream and downstream clamps. Make sure it's well supported, make sure there's no additional stress on the device, because that can affect the zero, which can then affect your performance down at the lower flow range of the device. So hopefully that helps.
Yeah, I'm being asked, one of the questions on here is asking about standards. So looking at the optimization of the instruments that we're using during, when we're calibrating a metering system or doing analysis, what standards is it based on in terms of testing and checks? I would guess there's a number of standards that we're referring.
There is. That's it, exactly. So in terms of our facility, we're an ISO 17025 facility. We have a calibration measurement capability as well that's underpins all our work. So that is traceable back to BIPM as well. So UCAS, in terms of our UK calibration, we're ISO 17025, and then our overall CMC values are submitted and reviewed by our fellow NMIs and DIs across the world. So that's all secured in terms of what we're doing in terms of our measurements. For flow meters, there's various different standards as well. So, for example, Coriolis meter 17090, differential pressure devices, ISO 5167, for example. There's various different ISO standards, and they mention how you should calibrate the device, how you should install it, how you should be operating the device. So that's if you're thinking of a specific technology, I would look at the standard. And we at NEL are involved in a lot of those standards. I represent NEL on API standards, ISO standards, British standards, Energy Institute as well. I also represent NEL at Euromet, Working Group Fluid Flow for BIPM, various different committees across the world. So we are heavily involved in influencing how people calibrate flow meters.
Okay. Right, I think I think we'll squeeze one more question in, and there is still loads coming in, so there'll be plenty to answer after this. Okay, one of the questions that's been posted is: should you perform a 0-point adjustment if you're changing fluids? So if you're going from one fuel gas to another, question. Should you? Yeah.
Yep. So again, it's a very good question. We recommend checking the zero. So there used to be a habit where folk would simply re-zero a device irrespective of whether it needed to be zeroed or not. So they might have changed temperature, might have changed pressure, it might just be a different day. So day 2 of a calibration compared to day 1, or they've changed fluid, like you mentioned. They wouldn't even check what the zero stability value was. They would simply just go up and re-zero it. Thankfully, we've moved on. This isn't the recommended process. We always recommend checking the zero. So what I would say is, if you've changed fluid, so from jet A1 to your alternative fluid, check the zero. Check to see, has it shifted? Is it still within the meter manufacturer specification? If it is, there's no need to re-zero it. However, if it's outside of the specification, yes, I would re-zero. So hopefully that helps. Again, I tried to cover that in the good practice guide. So again, I fully recommend that you download that. Okay. I think that's us.
No, that's
just
good.
In terms of my slide, I just wanted to mention one more thing, John. Just to let people know about upcoming events that we have here at NEL. So I'm also got quite a few different hats that I put on at NEL. I'm also the chairman or the chairperson of the Measurement Focus Group meetings. We run 4 of these Measurement Focus Group meetings across the UK. 3 of them are in Aberdeen and 1 is in England, typically. The one in England this year is in Birmingham on the 17th of May, so coming up this month. It's a free to attend event at the McDonald Burlington Hotel, a full day event from 9:30 a.m. to 3:30 p.m. and we've got 8 very good presentations. So I recommend you have a look on our website to see if you would like to register. And we also have 2 upcoming webinars from my colleagues. So one from Colin Lightbody on flow meter selection, and then another one from my colleague Harry in June. He'll be discussing a bit more about EPAT metering. So again, I touched upon EPAT a little here. He's going to discuss it a bit more detail and show some more results from that facility. So I recommend you register for those 2 upcoming webinars.
Excellent. All right, Chris, thanks for that. Yep, no, that's good. That's been a full presentation today.